Okay. Oh yeah, so music, right? So there's a link to it now on the tweets here. Yeah, we've been talking about patterns in music. We'll talk about contagion later on. So there's a tweet here about some crazy study involving 320 people and getting them drunk and seeing if they smiled more or less as a function of that. So apparently men smile more and imitate each other, and it's what's it called, the Deschelles smile. So whether you're really smiling or you're not, like where your eyes are, yeah. So people are coding this, they're watching people get drunk on tape. How do you do this? I mean, you just invite your Psychology 101 class to partake in an experiment. One side goes this way and the other one goes this way. Apparently, I looked at it a little bit, they rubbed vodka on one of them, on the one without alcohol, just so people didn't, they felt like they might be in the alcohol-based one. Because you don't want people to, right? You want to treat them so that they feel like they're in the same experience, of course, alcohol. Yeah, anyway, we'll talk about contagion, but this talks about, this sort of thing is rife contagion, right? You'll see that with war and unrest, people talking about contagion, things spreading. It's a huge, huge piece, so we'll get to that. And not just, of course, in social phenomena, but in diffusion. It's basic spreading, right? You have very elemental kinds of spreading. Yeah, so there's a couple of things. Oh, and so one of our fellow characters here, Charles Goodnight, who's in biology, just got himself a paper in Nature about group selection. So this is anathema to biologists traditionally, that in any way group selection would be part of evolution, because there's the selfish gene, for example, Dawkins' idea that it's just, we're just these big things that run around with the genes are actually being selected, and nothing else, there's no other level of selection. Anyway, so he'll probably get some hate for that by his friends. Okay, so good. Just telling you about tweets. All right, okay, fine. So, okay, so a lot of things to talk about here. But it really is these three big aspects. Where is it? Yeah. Right, so we're going to talk about generalized random networks, then small world networks, so this will take a little while. These are bigger stories. There's going to be a big experimental part to this, then a theoretical explanation story, and this is a mixture of empirical and theoretical, right? Okay, so random networks gone wild, and then small world networks and scale-free networks. So it's a huge deal. These are the things that have racked up 20,000 plus citations. Okay. I think broadly speaking, there are these. There are more, I suppose, in some ways, but these are some important models we'll be covering. As I've said, the random ones, the small world ones, and the scale-free ones. Small world networks will give you these generalized affiliation networks. Talk about that later. So there's a large community that works on so-called P-star models of networks. It's an enormous area. There's a lot of statistical, genuine statistical work on this. It's not kind of my cup of tea. I mean, it's okay. The problem with this is that you kind of create a black box. So here's an example network, right? You get a network. It's a social network, whatever it is. The power grid, something. You actually have a network. You're interested in it, and you want to do this thing of see, well, which part of network space is it in? What's adjacent to it, perhaps? And so it's a way of you have to choose the things you think are important. So, for instance, clustering. You could say clustering is important, or this term triadic closure, which is a ridiculous way of saying your friends know each other, right? So triadic closure is this thing that happens a lot in networks. People are introduced by an intermediate, or it could be some chemical thing, all sorts of stuff. So you have to say, I think these things are important. I think degree is important. And then you kind of create a black box which has little dials on it. And if you tune them the right way, you produce the network you've observed. And then if you tune away from it, you produce these kind of like a cloud of networks around it. And that can be useful. Again, this is creating an ensemble, which we'll talk about here. You're creating a kind of, you're sort of seeing what the kind of animals are around this animal that you have, right? You have this one example. The problem with this is ultimately, they have this word generative, but it's a little false in some ways because it's not a mechanism. It's not a mechanism you can go out and observe. It's just a statistical method for creating a kind of cloud of adjacent networks. So the dials don't have meaningful units. This is very important, right? So in a physical model, you have, say, viscosity in fluids or temperature. I mean, these are things you can control from the outside. These are, or measure. These are real aspects of the system. So these, in my opinion, kind of fail in this way. There's a whole bunch of people who would probably hate me for saying that. But that's it. Okay, so we're going to work on these guys. And the first bit is generalized random networks. Okay, so we've talked a little bit about random networks. You actually have 2 more problem sets that have been leaked onto the web, and you have 2 weeks for those, so it's okay. One of the questions in there, the first question deals with random networks, just pure random networks. Okay. I know you're so happy. Did I leave a bag out there? Do you think you could grab those 2 bags, please? Terribly sorry. I mean, it contains the food. I mean, that's the... Thank you, sorry. Very sorry, very kind. Okay, that's going to be important. All right, yeah. Okay, so... Oh, there we go. Okay, generalized random networks. All right, so you're going to think about random, the very beautiful things, okay, to play with mathematically. So, here's the generalization. We're going to now say, well, we have some degree distribution. We're going to fix it. And there are 2 ways we could think about this. We have a finite network, we have n nodes, and the nodes all have labels, right? There's Alfred and Barney, Kelvin with a C, right? So they're all labeled, and they have 7 friends, 3 friends, 4 friends. Those things are all prescribed, and that's all fixed. And then the thing you do is you jumble them around, right? You rewire these things, and I'll explain how to do that well, because you might think, oh, that's easy to do. But that takes a little thought. So you have, so this is a finite network, and you can make all sorts of random versions of it, right? The other way to go about this is to say, well, I have some beautiful, pristine, distribution that I'm going to select degrees from, right? That's infinite or whatever it is. Like it spans the whole thing. I'm going to select from that. So that's this example. Sort of go through here. So we're going to so we have n nodes, right? You're interested in a network that has n nodes. We're going to select degrees from our distribution. We've looked at a little bit of sampling from discrete distributions, right? I'll come back to that later. So you have to think about how to sample from it. And then we wire the nodes up randomly. So what's happening to start with? And I guess I have pictures, but I can't help myself. So you're sampling from some distribution, whatever it is. Could be anything you like. P of k, so we sample from this, we get some distribution, we get some value of k, and then we go out and we make a little node, and we'll say this is node 1, right? So we do it in order, and then we get another sample, so we get 3, and we'll say that this is node 2, and we go on and on until we get to node n. And now to randomly rewire, randomly wire, you're going to randomly select from all these degrees that are sitting here. I know I have this in my figures, so I can't help drawing it. So you're going to randomly select from these stubs. That's a kind of a bit of an embarrassing, kind of a, not good speak field, but stub. Okay, so you're going to choose from these stubs randomly, not from the nodes, but from the stubs floating around. Choose this one, and join them up. And you've got a whole vat of these things. So you go on and on and on, and hopefully you don't make any double loops or any of those things, but we can deal with those as well. And now you have a random network. Not quite, all right? So it turns out to be a little more complicated. But you could do this where you create your set of nodes, wire them up, and then take all the wires off, wire them up again, and then take them all off and wire them up again. You get a whole bunch, right? And in every network, node 1 has 1, 2, 3, 4, 5, 6, has 6 friends. Right? Node 2 has 3 friends. So they're all the same in that respect, but the wiring's randomized. So that feels pretty good. See, couldn't help myself. All right. So here are our first kinds of stubs, right? So no friends, 1 friend, 3 friends, 4, 5. And we have a whole bunch of them, and you're going to randomly select from these stubs. So of course, this one never gets connected. And as I said, you're not going to choose from the nodes. Depending on how you store it, you could kind of do the wrong thing. But you want a list of edges, or list of stubs, I should say, and then pick 2 of those and join them up. So this one gets connected to this one. You keep going. All right, so randomly select them, not the nodes. Must have an even number of stubs. So you might have to tweak things a little bit. And it's possible to start with that this guy could, these characters could connect to themselves, which you could just allow, or you may not like that. And if you don't like that, which we generally don't like, we'll fix it up. Okay, so, and there are various codes for doing this. I wrote all this C code that I put inside MATLAB for this, which works, but it's kind of a business. All right. Okay. So does this make sense? Yeah? You can sort of think about how you might do it algorithmically and cleanly. All right. So we could get these problems. So that's sort of phase 1. We'll call it phase 1. Phase 2, we go and find any of these characters and say, okay, we've got to scrub these out. This doesn't feel good. And it isn't, I mean, you won't get many of them, but yeah. All right. So immediately you see the problem, right? What we could do, what you might want to do is just like, this is really one edge, right? We could pick it up and then just put it somewhere else. That feels like a random reallocation of that edge. Same with this one. We've got 2 here, so we could just pick it up and go and put it somewhere else. But that's wrong, okay? That's because this one has to have degree 4. That's a fixed aspect of these. That's the one fixed thing about these networks. This is Frederick over here and Elspeth, right? And Elspeth always has to have 5 friends. If you take this one away and put it somewhere else, it's not going to work out. Agatha. All right. Does that make sense? Okay? Yeah? All right. So the simplest thing, so you can think about what we can do. So it's a bit funny. So let's look at this. So if we take it away, that's bad. If we take one end away, that's still bad, right? Because we're going to break that guy. We're going to help, this is going to be all right. Because it's still got 5 friends. Elspeth still has 5 friends, but this is waving around. So if we think of that, we're going to randomly reallocate this one, then somehow we have, at the same time, have to bring in one here. Okay, so there are a couple ways to think about how to do this. I did actually think of this myself and then was told it was a stupid idea and I didn't do it. Damn it. Santa Fe Institute years ago. Anyway, so then someone published like, oh my God. Okay. All right, so see? No citations. All right, so you have to have courage, people. Right, let's see. So here's an example of how we can tend to it. And you could think of ways to make this. And it isn't obvious that this doesn't mess up other aspects. That's the problem. Like, you want to keep it random. You don't want to create somehow something like more clustering or less clustering, like some other feature. So it's not obvious that this will do that. But let's see. Okay. So, we're worried about this, but I'm going to give you a process that randomly rewires any link, any couple of links in a good way, and we'll cater to those other ones. Turns out we have to use this more generally as well. All right, so let's see. So this character here has 3. This one has 4. We have 4 here and 3 here, right, in degree, right? So degree 3, degree 4, degree 4, degree 3. So we can't change that. We can't change that. Right? Xavier always has 3 friends, and that's it. So if we're going to break this one, then one way to do it is to think about, all right, well, let's randomly choose 2 edges, and if we rewire them like this, or we could do it like that, then we'll preserve the degrees at the nodes, and we'll have scrambled it a little bit. Yeah? Because these nodes, these 2 are not random with respect to each other. They're friends right now, and these 2 are friends. But these are just random edges somewhere in the whole network, right? So these things have no connection to each other. We have to be a little careful that this edge isn't this edge as well, right? So you want to make sure that's cool. So you just make sure that you have 2 nodes and 2 nodes that are not the same guys. So you want to make sure the edges are disjoint. Nodes that don't overlap. So we're going to rewire one edge this way, And again, this could be randomly chosen, but we rewire this one, rewire this guy. And that's not bad. We've preserved the degree, not just the degree distribution, but the explicit degrees. That's the thing. We're preserving the degrees of the individual nodes. But we're starting to shuffle it. So you can see if you kept doing this, you will start to kind of move through the space of random networks that have these fixed degrees for the nodes. So it just turns out you can't randomly rewire one edge. You have to do two at once. And you could think of this actually as, if you put dots here and dots here, this is a little cycle that's on, off, on, off. So you're finding any part of the network that's, or a graph, on, off, and then clocking it around one. Okay. Directedness, you have to think about that as well, but these are undirected ones. So you could say, well, I wonder what happens if you did, you can find a little 6 cycle that was on, off, and do that as well. That would start to permute it as well, but that's starting to be more unwieldy and messy. So this little algorithm, just a tiny little algorithm, is a good way to, given a network, to start to mess around with it, right? So you don't have to wire it up to start with. I mean, there's this one way of, you've got to create a network to start with, but if someone hands you a network, and they want you to randomize it, except for the degrees, this is what you do. Okay? You put it through a little machine that has this on the side of it. Not the toaster, this. Okay. And you can do this if you've got a little self loop or a repeated edge. You could do that as well, right? So you could say, let's specifically choose this one and some random other edge and do a rewiring like that. Right, so you could fix those guys up. It's not on the slide. Yeah, so it's the same as finding these on cycles and off cycles. All right? So you go through and purposely find any repeated wirings or loops and clean them up using this. It's a small thing. I mean, you could do it in different ways. But you're preserving the degrees. And then here's the extra part. So that was actually where people stopped to start with. This is work by Newman. So it makes a pretty random network, but you can actually see that it fails a little bit. It doesn't really give you every random. What you want is to create a box, right? So you've got a box that has, you reach inside it, and there's some degree distribution. You have a label on the side, so you don't get mixed up, and there's some degree distribution, right? So if you pull this box off the shelf and you reach inside it, you want that every network every configuration in this box has the same probability of being pulled out. There's going to be a lot of networks in there. So, you pull one out. You need that to be, if it's random, that's what randomness means, right? It means random selection by network. So you've got a bazillion networks. You want the chance of pulling out each one to be the same. So you need this little building process to do that for you, to make each one equally likely. Okay? Equiprobable. That's a fun word to say. Which I think is the only reason it exists. Okay, so rule of thumb, if you do this 10 times the number of edges, this rewiring 10 times the number of edges, then on average each edge has about 20 chances of being rewired, right? Because there's always 2 edges involved. But not 100 and not 1. So each one gets a chance to be rewired. Some can get stuck. You can have this problem of choosing, you can have failures to do things because you choose 2 edges that are right next to each other, or you move them in a way that you create a self loop, or there are reasons for why this thing can fail. And it depends on how nice the network is. So that will give you a randomized network. And I think that's really where I'm going to stop with this. In the next course, we talk a lot more about it. But this goes back to the motif story that we talked a little bit about. This is the way to generate these. Could add some more to that. Anyway, I think that's That's cool. So it's pretty simple. What else could you do? The nice thing about it is it exactly preserves the individual degrees of the nodes. Right? It's probabilistic, but it's not that probabilistic. It's not starting to kind of blur those pieces. So if you just pick up edges and you just pick up an edge wholesale and then randomly choose two nodes to place it at, you'll end up eventually dissolving the original degree distribution, and you'll get a plus-on degree distribution, because that's what if you really have random networks, that's what you get. So that's in the first assignment. But that's what happens if you just pick up an edge and throw it somewhere. You completely lose the original structure. That's too much. All right, small world networks. Okay, good. So this is a big business. I forgot to put my little thing on, didn't I? Is it alive? Does it live? Come on. Bad. All right, talking. Okay, so small worlds. All right, so this has been a part of my existence, but it's been a bigger part of some other people's. Wow, I mean, there are still papers appearing all the time, where the first thing they say is, I just want to find out if this is a small world network or not. And then my job is done. I'm like, no. So, wow, small world networks. All right, so social networks. So it's been a field in sociology, like a concrete quantitative field since the 1930s. I think I've mentioned this. So simply asking people who they know and who they've known in the past year, and all sorts of questions you can imagine. Schools are a good place to go and which kids are friends with whom, and you can create lists. Sort of thing happens more easily, of course, now with Facebook and so on. You can see who your kind of where individuals rank on each other's lists, right? So someone might be someone's best friend, but that's not going the other way. There's all sorts of things you can ask about this. Okay, yeah. Okay, so but they're really tricky problems. So how do you define, what's a friendship? How do you then encode that as a friendship? Right? What if you're looking at tweets between people? At what point are those people really, how do you count it? Of course, we have the idea of friendship and acquaintance, and they're a bit mushy, but you could measure, you could say, here's the rate of interaction between them, right? You could do this. Of course, there's self-report for small-scale studies. Just listing your friends is really hard. Generally, for people, it's hard. People you talk to regularly, and you leave off your mum or something, great. Let's see. And of course, then the remote sensing thing, which is what we and the NSA are all involved in now. That's opened up more and more and more just in the last 10 years, of course. Right? Dynamics, right? How do social movements begin? So people have been theorizing about this for a long time. They've been actively, of course, creating and stopping them for thousands of years. Collective problem solving. And this is still going on. I mean, of course, organizations are solving problems all the time, and there are really interesting things in, say, pure math now, which is a very, ethereal world of, which has, people talk all the time in pure math, but there's a lot of going off into a box and working for years without telling anyone what you're doing. It's still very important. But there have been some big problems solved on essentially kind of blogs. Someone says, "Oh, let's do this, people," and then they all jump on. So there are lots of interesting things here. Of course, we fail as well collectively to understand or choose the right thing or so on. Information, how does that move around? Right. So. Here we go. This is for the greater good, right? So the greater good. Which rules do you set up to have the best society? I mean, obviously, lots of places have tried. Various arguments for why you should have a king and queen have been put forward. Usually, when there is a king and queen nearby, probably feeding you. Philosophers come up with that one. Anyway, so democracy is the worst form of that sort of business, except worst form of government, except for all the others. Most of these things are attributed to Winston Churchill, but who knows who really said it. So what I'll call we're in the socio-technocene, is this thing I like to say. Socio-technical phenomena and algorithms. This is really, really incredibly interesting. People plus computation. There's crazy things are happening, and that Google is sort of this primary example, because the links are meaningful if people make them. That's sort of changing, I suppose, with more and more automated stuff. Hunch and crunch, or play and crunch. We're the hunch people. Computers crunch things. So this is just going to keep going on and on. All right, lots of things to think about. So here's a tiny little piece. It's about communication, search, and then allied with knowledge. Like where is the knowledge, or where is the sort of that's part of it too. You could think about search for information, which is another body of work, but you could ally it to that, I think. And of course, contagion is involved in here as well, spreading things, right? So you've got this big network. So can people connect through this network? And this is a distributed search, right? So you can have the detective kind of thing where someone goes online and then finds connections between people and tracks down someone a long way away, that sort of thing. But the question we'll ask is, can we do it in this distributed way, where you're allowed to, so you're given a target person somewhere, and I'll tell you the history. You're given a destination person who's supposed to receive your message, and you know something about them, which we'll talk about in various ways. So you know something about them, and you have to pass your message to some acquaintance of yours, who you hope will play the game as well. And then your role is finished. Right? So then they will participate, hopefully, and then that person will, they send it to someone, and so on. So it's this distributed search process. So lots of ability to fail in there. Someone just doesn't play the game. And we'll see that this actually leads to ideas for collective action. This has happened in the last few years. People have understood that this so-called small world business has implications for that. How do you organize and motivate and gather people around an issue? So marketing is not far away from all of this. All right, so here's the original study. So it was published in '69, and it's Migram, Stanley Migram, who most people know about because of his zapping of other people. You know about this? Yeah? Right? No? Okay, so I've got to tell you this little bit. So it's obedience to authority. So there are all these experiments, in the 50s and 60s, where the rules weren't quite as well laid out, and that's why we have IRBs, there's institutional review boards, which has been a big issue again recently with Facebook carrying out some experiments on whether happiness is contagious. Terrible experiment, just a terrible experiment. I mean, there are many layers to that, but one is, I will say there's an unethical aspect, but then the experiment itself was just awful. Anyway, so that's a huge other issue. So, it's still a problem. This is different to Facebook, of course, because the people may be getting tiny, tiny little shocks because they were messing with their feed. Here someone's hooked up to electrodes. Okay, so it's a little more serious. Well, so this is the way it works. So you really can't do this anymore. So you agree to be part of an experiment. You're a starving psychology student, and they say you're going to get pizza, usual ruse, and you come in the door, and there's another person who's part of the experiment. So you walk over, and there's a character with, and usually, I think they only did a few of these experiments. There's a reason why. Maybe even just sort of a day of it. Someone in a lab coat who explains the rules. So what's going to happen is, and there's actually this part of the structure here, so there are all these dials, these buttons you can push. You get to sit down, and you have this kind of a board in front of you with all of these buttons to push, and you're told that the other person's going to go into the other room and be hooked up with some electrodes, and they're going to answer questions. You're going to ask the question, they're going to answer. If they get it wrong, you have to zap them. And that's the game, right? So it turns out, of course, the other person is part of the, they're in on the experiment. They're actually an actor. You're the poor fool who is the person we experimented on. So, and it's all choreographed. So the questions they will get wrong are all lined up. So they get question 5 wrong or whatever it is. and you go, bzz, and they go, ah! There's a whole, even the yelling and screaming, like what they will do, is all lined up. So what happened was something, and I can't remember the numbers. You can actually find sort of long pieces on YouTube and nice descriptions of it, of a bad thing online, because it's quite famous. Something like 30% of people said this is wrong and just sort of left pretty quickly. But there are quite a few, like a large fraction just kept going. And the setup was that if you said, you sure? And there are videos of people saying this, like this is wrong, like this feels wrong. And the lab coat character, and this is why you're allowed to, you have to, this is one reason why in experiments on human subjects, it has to be very clear that they can leave at any point, right? You have to say you can leave at any point. You may eject from this experiment. If you don't like it, you can go, right? So that was not, of course, in any way conveyed, and it was much the opposite. It was, please continue. This guy, this sort of scientist just says, please continue. Just please continue. Yeah. And it was just, so it was authority. So it was just conveying authority. Yeah, yeah. And so they're like, okay, like I won't be responsible. They ask questions like this. And the screaming gets louder because the zapping is, you can see on this fake thing in front of you that the number is going up, like the intensity is going up. And there's a thing that says, don't go beyond this limit. And of course, people go beyond it, right? Warning could be fatal or whatever it said. There's something. And they're like, are you sure? And he's like, yes. And okay. So they keep going. And eventually the screaming stops. And they still keep going, right? Yeah. So it's very hard to believe. There was a French game show made up a couple of years ago, which was exactly this experiment. But they're like, hey, no one knows about this. And I won't do any Monty Python French accent. But they made with all, the whole set was all pretty spectacular and lights and the whole thing. And there's a crowd watching. And then someone has to sit there and basically do this to someone else. And that was a kind of experiment built into a reality TV show. Yeah, and I think the same kind of thing happened. You're on TV, it's even better. Some people definitely left. There's a few people left. So there are a lot of these experiments that are famous. There's the social conformity one. This is the Ash experiment, where again all these Confederates, right? So there were like 10 people in a circle, and this is a little milder, but you see on a projector these 3 lines, and then over here another line, something like this, and you have to say which line is it A, B, and C is the same length as the one on the left or the right. That's it. And it was these are always far enough apart that it was obvious. Like if you did this in isolation, it was obvious that it's B or whatever it was. Like no one would ever get any of the questions wrong. Would never get any questions wrong. And they ask the people in sequence which one they thought it was. Sometimes you were the last one. Sometimes you were the 4th person or the 5th person. But every now and then you'd be the last one, and all of these other people would say the wrong thing. And there's a good fraction of people, like a very large fraction of people, who would agree with them. And there's been recent neuroscience kind of like MRI studies that suggest that there are roughly two kind of ways that people react to this. One is, oh, I'm wrong, like I'm wrong, I'm wrong, and all these people are right. And others are like crowds of crazy, these people are crazy, but I'm just going to say what they say because who knows what's going to happen. So, they survive humanity by running with those guys. Everyone's running that direction. Okay, what are we running from? Or two, yeah, right. Which can end badly, right? The whole, larger numbers of humans. Yeah, I mean, the thing is 1 billion people can be wrong, right? So, about whatever it is. Miley Cyrus or something. Okay, Crocs, also good. Well, they are comfortable, it's tricky. All right, let's see. Okay, so lots of fun experiments. So he did lots of odd things. And he was at Harvard for a while and different places. That's important, actually, the Harvard bit. He did another one where, I'll tell you a few others because these are fun, where he sent graduate students out to the T, so this is in Boston, to the T, and for whatever reason asked them to walk up to people sitting down and say, can I have your seat, please? Just do this and just see what happened, and then later on just see what happened, right? And so they're graduate students, they're full of pizza, but they're healthy-looking people, right? And, it's not, because, right, that's a circumstance, like maybe, someone has, they've got crutches, or there's some reason that you can sort of see that they might ask for the seat. And these people aren't sitting in seats that say, please give up. So the thing that they came back with was, and I can't remember the numbers, but they basically said that people would do it, but it was awful to do. It was awful to ask these people. And then Milgram's like, you're weak, what's wrong with you? And he went out and did it himself, and it was very painful. It was very painful, because it's just outright lying to. So I don't know if they ever published that, but there's a bunch of things like that. They have one where they did, so they set up an apartment across the street, and on this side, they'd have, again, graduate students who would walk and then look up in the sky, right? And then just see how many people would also then count the numbers of people who would look up in the sky. And what if you have two people doing it, right? You have two people going like this, and right, how many do you need to get everyone to, oh yeah, right, and this one, if you just had one other person disagree with the majority, then it was fine. Then you're like, okay, I'm not insane. These people are insane. But there's one other person, and I'm with that person. We've tried to, and if anyone's interested, we've tried to build experiments that are much more ambiguous, but have a correct answer. So, and I actually made this. I forgot about this prototype kind of web experiment where there were, even very ambiguous things where there isn't a correct answer, like which painting is more beautiful or something, and then dialing the social pressure on the side. Not in an evil, illegal way, using correct answers from before, but this is what the previous people have said, like at what point do you tip. So this is something where it's not ambiguous at all, but under extreme pressure, in a sense, you'll get people to agree. What happens when it's more ambiguous? And so you know it's going to be easier to shift people, but as you have to measure the strength of the ambiguity, which is hard. You want some dial there. Yeah, so if there's really nothing you can see in front of you, that an individual making the judgment by themselves would be able to sort out, then it's different. So we'll get to that a little bit later on too, when we look at fame and why things take off. So there are some things that take off that by themselves, a lot of it is social conformity. Did we have a statement from the crowd? No. Good. I want to make sure we're happy, people. I brought, I've dried peaches. Is that good? Sugar. That should be safe. And there's no shortage of objects here. I like mango, actually. So that. You have that? That's just chocolate with just raspberry goo inside it. If that's no good.
Yeah, I can have raspberry ice.
Okay, good for you. Just eat as much as you want, basically. Okay. As you need. The cross-country run is dangerous. It's all gone. Okay, so, all right, so let's talk about this experiment. So, Milgram, yeah, very creative, lots of ideas. Some didn't work. This experiment is complicated. It's one that, this is the one I'll tell you about, was successful. He tried this a few other times. It didn't work out. He didn't publish those ones. They were sort of dug up in his collected sort of boxes of work later on by someone who went through all his stuff. So there's a little bit of that. It's sort of like the statistical significance thing. So significance is a terrible word to have used for statistical significance. It's a disaster. But the 5% threshold, right? So if you have a p-value that's less than 0.05, you're like, it is statistically significant. Which means that 1 in 20 works is wrong, right? Because if you can put them all together, then anyway. But the framing is terrible. Okay, so here's this experiment. So this is the thing about the small world. That tells me to feed you. All right. Head of the game. So Milgram was thinking about this notion that people say, oh, it's a small world, right? So you meet someone, you talk a little bit, and then you have a friend in common, or you both like something much more mild, like you're both fans of the Red Sox. People find something in common, but often this is about people. You know such and such, who knows such and such, and they know this person, right? And that's often a surprising thing, and people will say it's a small world. So Disney makes a theme. There's a whole little park associated with this. So and songs. So it's a small world phenomenon, or sometimes called 6 degrees of separation. 6 degrees of separation. The idea being, so this has a long history. The idea is that an odd kind of history that for the whole Earth, on average, people are only 6 steps away from each other. You know someone who knows someone who knows someone who knows someone. On average, you can get to anywhere else on the planet in the world's population with 6 steps. Now, this continues to fascinate. There was a few years ago, there was a Facebook study. I mean, not particularly great, sort of a fun thing, but just basically looking at this giant Facebook graph that they have, which is enormous. And I think they ended up with 4 or something like that, the average separation. Now, you can think about friendship, like how strong are these connections, all these things. This was an experimental attack on it, so it's a clever thing. So I have to kind of explain this a little bit. About 300 participants, and the way it was done was to give people a nice little passport thing. This is again in the 60s. This is before, there was junk mail, but not perhaps as much as they came to be. So you're given this nice little passport, which had postcards inside it. And as the first person, you're recruited. So there were different kinds of recruiting. One was word of mouth. Another was soliciting people through newspaper ads. So there were a couple of different batches of people in, 2 in Omaha and 1 in Boston to make 300 people. So you get this little passport, and you're told about this person that you're supposed to get this passport to, right? So you're given this information. So you're actually given their name, where they lived, which was Sharon, Massachusetts. I think that they were a stockbroker. Maybe even something as ridiculous as more specific than just the city they lived in, right? So it's you're given a fair amount of information. So their work, where they live, and their name. And this is a long time before Google and so on, but you could imagine someone could go to some lengths to call people and try to figure it out. But that was not the idea. You were told to send this passport in the mail to someone you thought was closer than you to this person. Of course, if you know them, you send it directly to them. And I can't remember the wording, but there was a restriction on how well you know them, right? So you should be able to recognize each other in the street, for example, something like that. We've talked a little bit about strength of tie. So there's that. And so then you're further away from it, right? So someone sends this passport to you, you get it, and you read the instructions, and maybe you call them, the person who sent it to you. You look inside it, and if you participate and send it on, there was a page to pull out, which I guess was kind of a postcard, and you could send that back to Migram. So it's being traced along. So even the ones that fail, if they get 5 steps and they fail, you'll have the 4 where it went in those 4 steps beforehand. So that was a nice bit of design. People were pretty compliant. I'll say this again. I think 75% of the time people would actually send it on, which is kind of amazing. Response rates to surveys and things now, especially on the web, are like 1%. Whoever responds to spam, very special people. They're like 1 in a million humans that keep it going. I don't know what the rate is. What is it? You know those people? Well, they're killing us, right?
Who responds to this?
Someone does. Some magical person does. Probably, and then 1 out of 100 of those are not accidental clicks. They're like, yes, I want to.
Here's my bank account.
I've invested some money with a prince, West African prince. Someone is doing something wrong there. Anyway, maybe, I don't know what's, okay, so, all right, 20% of them got through, which is pretty good, because the thing to think about here, if you've got a 75% chance, right, 0.75 times 0.75 times 0.75, so it's an exponential decay. Of the fraction that are getting through. So you have kind of a hard problem, actually. right? And you were only allowed to send it to one person. So it's not spreading, right? So you're not getting any gain like that. So it's a pretty brittle kind of thing. And then the upshot was that the average length of chain was 6.5. So this is not where this 6 degrees comes from, actually. That comes from before. There's a play by John Gare, I think you say his name, which was called 6 Degrees of Separation, and which sort of danced around this idea a little bit. And that was in the 60s as well. But then there's a Hungarian author, poet in the 20s who sort of just said this. He just said, oh, this is a beautiful idea. And as far as anyone knows, that's where it kind of comes from. Right. So here's a sort of little bit of happenstance that this 6, which just was popped out of someone's crazy head at some point. It's like, okay. Seemed to be somewhat confirmed with this simple experiment. And of course, it's just in the US. It's just a particular time of the world. And one thing one aspect we'll deal with a little bit, the chain length is 6.5, that's for the successful ones. Right, so there are these unsuccessful ones which stop for all sorts of reasons, randomness, people couldn't be bothered. If they'd also been motivated to do it, and motivation becomes the big issue that we'll get to for the social movement thing. If motivation was involved, then people may well have, this average chain length could be larger, and so we'll look at that as well later on. There's a way of thinking about that. Of course, because you have the distribution of chains that failed. You have the distribution of their sizes. Right? There's some that failed after 1 step, 2 steps, 3 steps. You know something about them. All right, so lots of popularization. We talked about it's a game. There's the Kevin Bacon thing. So I'll give you more background because it's fun. All right, so we talked about this. Right, so if someone's in a movie with Kevin Bacon, they have a Bacon number 1. And then if you're not in a movie with him, and then if you've been in a movie with someone who's been in a movie with him, this becomes hard to say, you get a Bacon number 2, and so on. So we have the ridiculous movie thing, and of course, if you're just in a movie with someone else, you're tied to them. So if you think about the movie actor network, it's the strength of the ties, they're not in there. What it means is each movie produces a little fully connected network. Right? Everyone who's in that movie is connected to everyone else. So you get all these kind of balls of fully connected, right? Which is a bit funny. So if you're a bit player, then people say, well, do they have a line or not? Right? Extras. Yeah, Ricky Gervais. That was an important aspect in that. Do you have a line? Okay. So Paul Erdos, who's famous for being right out on the spectrum for pure math, sort of traveled around the world with a suitcase and basically just did math all the time. And speed, actually, right, also good, yeah. Which he went off, the story is he went off it for a month, and that wasn't good for his productivity, and he said, this hurt, I don't want you to do that. This hurt mathematics, set mathematics back. So he resumed the dosage. All right, so there's an Erdos number. Mathematicians love this sort of thing. There's a whole kind of like a vampire cult with pure mathematicians, right? Because they've got the breeding thing, like who sired whom sort of business. There's the mathematical genealogy project. There's no one else is involved in this. It's just the math. Like, so you can if you connect back, you can go back to whoever it is, Euler and so on, or Kronecker or someone, and you can get your thing printed out that shows your genealogy in math. Who was your advisor and who was their advisor. Yeah. Because it matters. We need to know if you're a pure blood. Yeah. Not like these filthy scientists. All right. It's pretty funny. Okay. Vampires. All right, so there's an Erdos number that's just for fun. It's very good with graphs, of course, so he liked this sort of thing. And then you're allowed to have the Erdos-Bacon number, so you can click on these things. We'll call it the EBN. So actually one of our members of the Computational Story Lab has a Erdos-Bacon number less than infinity. Most of us are strongly sitting at infinity. You have to be in a film. So I guess I'm not going to say it, but she was accidentally, well, I mean, she tried out for it, but she was living in the Dominican Republic, is that right? I think, or Dominica, and there was a Spanish film that appeared. They turn up, a Spanish film outfit turns up, and they're going to make a film, and she tried out for a part, so she's in this part. So Isabella Rossellini's in it. I mean, it's a good film. She was the mistress of the evil dictator. I don't know if she got killed. Anyway, but she had some lines. Anyway, so and of course she's published, so yeah, she's in there with less than 10. It's not bad. Natalie Portman, in fact, who has a bunch of Hirschlag is her original name. So she has a bunch of papers in neuroscience or something like that at Harvard. She was there for a little while, so she has 5 or 6 papers. So she gets in the list. Good Will Hunting. Okay, so this is just a little personal history. So Dan Kleitman, very famous character again, who's one of the sort of founders of combinatorics, big branch of it, was at MIT, and I remember coming into the MIT, so combinatorics is an applied math at MIT, it just is, and coming into the pretty terrible applied math common room, which was sort of basically looked like it did in the 1950s, as far as I can tell. And seeing one day, and I'm sure as I recall, it was him talking to these 4 guys in suits. So this is obviously strange to start with. They're sitting around, and they're dressed extremely well. So something is very strange, right? They don't look like policemen. I mean, it's a good conversation, or federal agents or something. So I'm trying to figure out what's going on, and I didn't quite get it at the time, but he's like demonstrating some stuff on the board, and they're like, yeah, it's fantastic, And they're incredibly good-looking people as well, like it's all wrong, it's like their hair is good, so something's really wrong. And he said one of his things that he was famous for that I recall was giving a seminar where you have a stack of papers and just pull one off and say, oh, this is wrong, and then just fix it up. And he could play the whole professor thing pretty well. Anyway, this ended up being his board. So it was Ben Affleck, and those characters, who then proceeded to make terrible films for a long time, but now seems to be on an upswing. You couldn't trust him for a while, but now he seems to be on an upswing. So so that's and combinatorics kind of has this feel that maybe you could do it. You could be a savant. There are certainly realms of pure math that you have to climb a giant mountain, and they're sort of going to promise you that at the end you can add to that mountain, but you could fall off in a horrible avalanche at some point. But it's counting stuff is fun. There are triangles and numbers and things, and you kind of get into it. So it's sort of plausible, but that this could have been true. Anyway, so he has an Erdos Baker number of as a result, because he was an extra in this. You see him walking around in a couple of different places, like going this way and that way in Harvard Square. So he has 1 for his papers with Erdos, and then 2 because Minnie Driver was in this, and then she was in I don't know which film, some other film with Kevin Bacon. So 3 is pretty low. So Strogatz is in there trying to get himself down to some number. He might be a 3 as well. Anyway, of course, this is all on Wikipedia. They got to write about it. All right. So good thing to know. So 3 degrees. So 6 is a huge number. This is an important thing. 6 is a huge number in a network. It's a big number. It's a little number when you look at numbers. 6 is one of the smaller ones. Just kind of you feel for 6 is that's not very big, right? 6 degrees of separation sounds like you're just best friends with the president sort of business, right? And you're not far away. You're in the same school, but it's a pretty vast distance actually in a graph, and so that slips by people's heads. I mean, in this case, this was this story that emerged with the NSA, and this is when is this? This is just last year. Was like we're only going out to 3 degrees of separation, only 3, right? 6 is right, only 3. But that really hoovers up a tremendous number. I mean, there are estimates of how many friends people have that sociologists have carried out over the years. They range quite a bit, but sort of hundreds to 1,000 kind of thing that people you really know can keep in your head. There's the Dunbar number, which is 150, which is an estimate of what people can handle in their heads. There are Dunbar numbers for all organisms too, right? Whales have a number, and people have been able to measure them for different things. Very cool stuff. Let's see. So that sounds like it's not much, but it's a lot. So if you go out to say you have 100 friends and they have 100 friends, and of course there's some overlap and so on, but that's already 10,000 people if you can trade. So that's a lot. Anyway, good to know. Good to know. Where was this? This is wired. No, is this wired? Doesn't matter, I guess. But they got the right kind of image here. Yeah. All right. Okay. Yeah? Yeah? You can keep eating. 15 minutes. Very blatant, Not even pretending. Okay, so here's some actual work. Let's go back to some work. All right. So there's been a lot of fascination with this for a long time, for sure. It's kind of a cute story. It's fun. But we'll see it actually has all sorts of things. So let's just get at this experiment, and I'll start to tell you about an experiment we ran next. So this is 1969. It's Travis and Migram. And these are the successful chains. So this is a distribution of the successful chains. So someone knew someone who knew the target. There were actually 2 of those. And 100 of these started in Boston. So maybe you knew a stockbroker, for example, and you just like, that's enough. You're like, okay, send your thing to them. So that's at the scale of the world, that's probably unlikely. There are some that took 11 hops, which is, impressive that it lasted, being sent and sent and sent. Yeah? These nice little passports. So this is some story. So the average of this is 6.5. Okay, let's think about how this thing could work. So there are 2 pieces. Short paths exist, and this is the thing that people got stuck on for a long, long time. Fair enough. It's a geometric aspect of the network, very quantifiable. And then there's this, and so it took a little bit longer, well, not much, for a year or 2. John Kleinberg, who I've mentioned, was the character who sort of made this clear. Yes, people know about it, but he made it very clear. The people are good at finding those short paths. They don't have to find the shortest path, but they're able to find relatively short paths. And the issue is with this failure as well. If there's a say a 50% chance that next person will comply, and then the 50% chance of the next, then you're in trouble, right? Your chance of getting through goes down with the length. So you do want to find a short path, and we'll see how people who are good at doing this did this. But it doesn't have to be the shortest path, of course. So we have a geometric aspect to these networks, and then we have this algorithmic piece on top. So this becomes the crucial thing. So what we'll actually see with that first paper, the 20,000 plus citation paper, was really about this part, actually. And then this comes along afterwards. There are all sorts of fantastic things that come out of just the geometric aspect of this, that there are short paths, and the way to think about it, the way to operationalize is a terrible word. To quantify it is to think about the average shortest path distance between all pairs in a network. Mm-hmm. All right, so we ran an experiment. This is actually an attempt to make the thing look good. This is, of course, 2002 or 3, and there was sort of this idea of someone going from India to the US. By this point, we kind of actually had paid someone to make this site. But the first site, that's behind all this, was published in 2003, was a horrible mess of Perl and like 1995 style website. We had a few little graphics and things, but it was pretty horrendous. So we made this experiment. You could sign up. What am I going to tell you? Yeah, you could. So we did pretty well. We ended up with 60,000 participants, which is really fantastic for these online experiments. In the list of online academic experiments, it's kind of one of the first big ones, perhaps. And this is what we did. So let me tell you a few things. So we ended up with 18 targets instead of just one target person. And I'll connect this into all sorts of other work later on. We had a professor at an Ivy League university. Pretty random things. Archival inspector in Estonia. This is basically all you were told. You were given this information. Their name, of course, what they did, and the city and country they lived in. We had a policeman in Australia. We had a a potter in New Zealand. There was a veterinarian in the Norwegian army. So we had a librarian in Paris. So what happened to start with was we were lucky. We ended up with 24,000 chains being started, right? So 60,000 people spread across these chains. There was some contagiousness involved. We were very lucky. So we ended up with, we had a piece in this defunct section called Circuits, 2001, like the 12th page of this thing. And it was about this little experiment we were trying to run. And that article got picked up everywhere. And then suddenly we got a ton of people, which broke the thing we had to pieces. And we had to fix it up. I had to come in on Sundays if the computer just crashed, because it was just some box called smallworld.columbia.edu. And it would just like give up. It was terrible. It was pretty bad. There was a MySQL database that was good of us to do that, and but the Perl kind of like doing horrible things. So to start with, though, we did a bad thing. We used a little spider to try and get email addresses. I mean, this is just embarrassing, but it's 2001, and I'm like, okay, so we found out a way, like, how do we get email addresses, right? So we're like, okay, I guess this is the way they do it. And there were these programs that said, they would actually return, you'd put in a city, and they would claim to return email addresses for people in that city. So you put in the number you want, and it would chug away and give you these things, and most of them, of course, didn't work. It was a total lie. The funny thing about it was it only worked on Windows, so I had to get this laptop, and we sort of put it in this little hermetically sealed box and ran it over there. Anyway, so we thought we were sending off emails to Seattle or Los Angeles or something. We'd push a button, and it would send 10,000 emails off. It was dubious, but we're trying to recruit people. And they got an email that said, here, log in, and you can start a thing. And that was it, right? So, of course, most people ignored it. But we got a few people trickling in that way, but then this really made it take off. It was terribly, there was just such bad things we did. So if you came to the site and signed up, then people still do this. You get an email with a password, and then you could log in and all this sorts of stuff. So as I said, we ended up with that many targets. To start with, we only had 5 or 6. These were people we knew. We asked them, and they're like, sure. So there's some random people involved. And then some were in Australia, some were in, there's one in Indonesia. So Robi Muhammad is the graduate student involved here. He's from Indonesia. So he had, this character was hard to find. He was an unemployed person in Indonesia at the time. He was super hard to find. So I guess I'll say this again, but the professor, the Ivy League professor was most reachable. And so this goes to motivation eventually, in that, so you know the name, you know the place they're at, and so on. You might not know them, of course, but you could see that path. You could see how that would work, right? People wanted control over this whole thing, and if you could see that you could send it to someone who was in a college somewhere, then maybe you could see how it could work. But getting it around the other side of the world, that's harder. So we tracked all sorts of things. We tracked, where the chain started from, which country in the world. We had, does it say? 166 countries, right? It did spread tremendously. We had someone in Novosibirsk in Russia. So that was a good person. That was a college student out there. The way we recruited the rest of these targets, these are the people we didn't know, we simply put a thing on the site when it was starting to work. And we got 5,000 or 6,000 people who wanted to be targets in this experiment. All right. And we chose, some interesting characters, some hard to find characters. So here's the full thing. Yeah, right. So I've listed some of them. We had a journalist in New York City. That's true. We had a writer in New York City. Yeah. It's an old friend of my wife's. Novosibirsk was a PhD student. There was a student in Croatia. Again, hard to find. We had a journalist in Germany. We had a retired person in the UK. That was hard. That was definitely hard to get to. All right. So any others? Yeah, someone in life insurance in Omaha. That was kind of good. All right. Yeah. So and there are more details here, but how many chains started, the success rate, the average path length, and so on. So I'll talk about that more generally. So here's the big problem is, now it's email. So we're using email, right? And we did we did bad things, like we made the email look like it came from their email address to make it feel like, that was really from them. We did pretty well. We actually had a 37% participation rate, which didn't really change much. So there's an initial one, the person who started it might kind of have some more pressure on the first person they send it to. They might email them separately and so on. But as you moved away from that, you forget about the initiating point. You have no idea you could actually look up where it started. We made a little tracker thing. You could see where your chain was going. That broke sometimes. Anyway, so you could see after that first couple of steps that it was about 37% on average, because it's just sort of out, you've forgotten about the start of it. Everyone is basically just receiving an email in this experiment. So here's the problem. So if you have 10 steps, the chance, you're only going to get one in 100,000 through if 37% comply at each stage, so 37% is fantastic. I mean, that compared well to normal responses to surveys, which are sort of less than 1%. People really enjoy this. We gave them nothing. At the end we said thank you, and we gave them nothing. Oh, we did give them eventually this ability to look at which, as I said, was pretty broken. But you could see how it tracked. And there was some interesting kinds of paths. I mean, there was one that, for instance, that got to Australia, bubbled around Australia, and then went back to Canada, and then went back to Australia. I mean, people move around in interesting ways. There was one that went from, I think, the UK to Uganda to Moscow to Novosibirsk. Like it went, whoop, whoop, whoop. You send it to people have all sorts of reasons for sending them, and we'll get to that when I talk about this some more soon. But we ended up with, out of all those chains, a little less than 400 completed. So we didn't have, Migram had 20%, we had 1.6%. And it really took us a while to understand that this makes complete sense, right? That failure rate is so high, and we made it's a brittle experiment. We were just trying to mimic Milgram's experiment and put it into an email version. Of course, you can make a tweet version right now. But this gets lost a little bit. This is an algorithmic process, right? You're trying to actually do something. You're trying to navigate through this social network. It does fall back, and people say, oh, well, let's just look at the average path length between people. So that's the issue of whether people can actually navigate this thing, and navigability is the word that Kleinberg used. That can easily be lost, but that's really a key thing. I want to say we did get some letters from people and who want us to find people. So this is before Facebook. There were sort of dubious kind of classmates sites, those sorts of, like, find your classmates. The ads are always really, they feel like they're trying to trick you. They kind of bubble. And then Facebook kind of killed that, I'm sure. It must have, yeah. But it's way before that, and it's way before Twitter and so on. If we were smarter, we would have we might have built something. Yeah. No, but actually we wrote proposals. I mean, I can show you proposals of what we were doing for this, and I actually have a Twitter account now, Collective Detectives, right? Well, I'll tell you a little bit more. So the Boston bombings is actually a relevant example here. So. Yeah, I mean, the thing that stopped us back then was stalking, right? Like, or I don't know, mafia. Like, hey, could you find this guy for us? And okay, here's an algorithm, sure. Yeah, and then it's distributed, right? It's like you're passing the message on. I mean, you could make something say, well, if you don't want to be found, just ignore this. But it seemed like it could be used to bad ends. We got a letter from a fellow in England who sent a copy of it's very sad. He sent a copy of a newspaper article from the 1950s. His brother had disappeared in Italy. And he said, can you find, like he wanted to see if we could find him. On a much lighter note, there was a woman who said she met a guy at a rugby match somewhere in, God knows where, like South Africa or something. And she didn't know his name, but she wanted to see him again. So like this is some sort of, right. So what was Yeah, well, actually, the thing at the time was Friendster, I think, was the... Friendster still exists. It's out there with MySpace, like, just kind of like hanging out by themselves. So that did exist, yeah, which was purely about, right, yeah. No, it's clear that you can harness this for good and for bad. But it is about motivation, so how much do people want? So there's also reward, right? So that was something we never figured out, and I'll show you these guys later on for a social action kind of problem was, I mean, what it becomes social action, but is very much it's actually to do with the advent of the internet in a funny way, so I'll tell you about that. But they solved this incentive problem. So people could game this, right? So say you're going to give someone $10 if they're part of a successful chain. Well, then you just make 100 accounts, and you found the person you're going to send it to, and then you just you get 100 accounts in the middle, and then send it. I mean, so you have to worry about that. So that's a thing to think about. How do you reward people for successfully using this to find something, let's say good. Let's say find something good. That's an issue. Anyway, so this is the last piece perhaps to add to that. So motivation matters a lot if the target seems reachable, which was true of the Ivy League professor, less true of some of these characters who were it's just harder to imagine that you would have a connection. So you can get very small changes in these attrition rates, right? So 37% was the average, but if you go from 40 to 30, for example, or drop 15, there's an example, drop 15% in attrition rate, you could decrease your, well, attrition means the rate at which it's the opposite of what I was saying. Attrition rate is the amount, so ours was 63% attrition rate. So if that jumped up to 78, more of them are being lost, then you can get a huge increase in completion rate after 10 steps, for example. I need to say exactly what that is. But, all right, so I'm going to talk more about that when we reconvene for this business.